Today we're going to talk about the length of a polar curve and the surface area of a revolved polar curve. Okay, so the first thing we're working on is the length, and then we'll move to surface area of a revolved polar curve. So to do this, what we're going to talk about first, okay, is r as a function of theta. Okay, theta usually is denoted by alpha and beta as the upper and lower limits of the integral. Okay, but we're going to start with our parametric equation. So our parametric equation, it is described first by the relationship between the polar coordinates and the coordinate axis. Okay, I got r is equal to cosine theta, or y is equal to r sine theta. Then this is going to be, if r is a function of x, we're going to substitute that right in there. Okay, and we get f of theta times cosine theta and f of theta times sine theta. Okay, these are actually parametric equations where theta is now the input. Okay, so if you remember before, we started with our equation for a length of the curve from A to B. Okay, and we can change this, and we use T for parametric equations last time. This time we're going to use theta. Okay, so what we want to do, okay, is we want to take the derivative. We want to find dx d theta and dy d theta. Okay, to find dx d theta, okay, we end up having r negative sine theta, cosine theta, dr d theta by the chain rule. Okay, so the product rule and then the chain rule here, and then the product rule again, and then the chain rule. So putting these together, if I square dx d theta and if I square dy d theta, I end up with, and you can pause the video and kind of walk through these two things. I end up with these two pretty big expressions. Okay, but the trick is here, if we add those together, you'll notice that there's like terms here. Okay, and we end up with an expression that looks something like this. So what we can do is we can substitute that back in, okay, to our dx d theta square, dx d theta and dy d theta. So it's this piece of the parametric integral and this piece, okay, and we end up getting this integral here. Okay, now we can do a little bit of simplifying. Okay, you'll notice this is going to be 1. Okay, you'll notice this is going to be 1, and then we end up with a length equation using an integral. Okay, and now we have r and theta as our two variables. Okay, so this is the same thing. If you remember from the previous sections, we talked about the arc length is equal to the integral of ds, and our ds is changing, okay, to a different format. So that's one way of remembering it. So we're going to use that for our polar graphs because now it's in terms of r and theta. So an example, we want to find the length of r is equal to 1 minus cosine theta. A lot of times these are going to be calculator problems because trying to find the intersections can be a little difficult. Okay, so our first is to write off the integral, okay, and then substitute r in here, okay, and then take the derivative and plug it in here. Okay, and again, I throw this in my calculator and you get your answer to be 8. Okay, so that's an quick example of how to find the length, okay, of a polar curve. Okay, now pretty simple. Okay, moving on to a little bit more of a AP type of question. This one says find the length of the inner loop of r is equal to 3 minus 4 cosine theta. So if we're to graph 3 minus cosine theta, I'd end up with this graph right over here on the side. Okay, and the inner loop is just this little piece right here. So I want to find out what the length of that inner loop is. But the problem is we know that the polar curve starts at a specific place and ends at a specific place. Okay, so really this inner loop, okay, I kind of blew it up here. Okay, and by symmetry, if I can find the length of this, okay, this little piece right here, okay, I would multiply by 2 and find the length of the top piece. Okay, to kind of put that in a little bit more perspective, okay, if I were to look at the graph of this thing, okay, it starts by plotting here and it goes through the pole, and then I have to wait for it to go all the way around to the other side to get that second half. But all I really need to do is focus on is this first piece. If I can find the length from here to here and then multiply by 2, that's going to give me the length of the inner loop. So back to our equations. So by symmetry, I can say this, okay? And back up here, I'm just gonna say, hey, the integral, okay, from here, from 0 to, and then I found this 0.7, so it's when it crosses the pole here, okay? And that's when it's gonna be equal to 0. When the r is 0, I can figure that the first time that's gonna happen is 0.727, okay? Now, I would probably want to use this as my exact answer, okay? 3 decimal places, 4 decimal places is a good approximation. So then I go back to my equation. Okay, here's my r, here's my drd theta, okay, and I can plug that in. Or I could expand it out if I wanted to, okay? So some people like expanding it out. Okay, if I have a calculator, there's really no point in doing this. Okay, if you have no calculator, you probably need to expand it out and cancel some stuff. Okay, so here I'm going to again multiply by 2 because I'm doubling the length of this little half piece that I have down here. Okay, and then you could expand a little bit more. Now the reason I reduced this for you guys is that this could be the multiple choice answer in an AP test. Okay, so that the whole integral could be your answer. Okay? Now if you did throw it in your calculator, you'd end up getting approximately 2.407. So that's kind of a tricky way of asking a length equation in terms of theta. All right, let's move on to surface area. So surface area, our equation we have is r is equal to 4 cosine 9 theta. So r is equal to 4 cosine 9 theta would be this flower looking shape here. Okay? So we want it, now it's this whole thing. Now we're not going to revolve the whole thing. Okay, it's going to be a little more specific in the question. So it says between 0 and pi over 18 revolve around the x-axis. Okay, so I know that 9 pi gives me intervals of 90 degrees over 9 or 10 degrees. Okay, so that first little piece that I have on my graph, okay, is this from here to here. Okay, going from the first piece, okay, which is 4, okay, all the way to the polar origin. Okay, and I'm going to take that piece and I'm going to revolve around the axis. So going back and talking about the our rho ds equation, okay, it's going to be 2 pi rho ds. Okay, our rho in this case is the distance away from the axis. So my rho is going to be a y measurement, okay? It's going to be a y measurement. And then I have my ds that I just talked about from above, which is r squared plus drd theta squared d theta. Okay, so now I got my 2 pi, I got my y, okay, which is r sine theta. Okay, that's the general form. Okay, and then I can just substitute in my function, its derivative in there. Okay, and you could factor out if you wanted to. Okay, but most likely this would be a calculator question. The only trick though is that this r, you have to substitute the original equation in. There's my sine theta. Okay, and then everything actually in this integrand is in terms of theta. Okay, it's pretty complex to type this in your calculator, but you should be able to. Okay, and you should get your answer to be 4.421. So that's the surface area. So this line segment, okay, from 0 to pi over 18, being revolved around the axis, okay, would give me a football-looking shape. The surface area of that football-looking shape would be 4.421.